Hello everyone. Let us have a look at a one-page summary of the chapter on momentum, impulse and collisions before we move on to some exercises. So we have defined the momentum as mass times velocity and have seen that the rate of change of momentum is equal to the net force. Therefore, this was a reformulation of Newton's second law. We also looked at the time integral of the force over a finite interval, which gave us the quantity called impulse, and this was also equal to the change in momentum. We said that the conservation of momentum for a system of particles is a very useful concept. So therefore, we defined the total momentum of a system of particles as the sum of their individual momenta. And we noted that if the total external force on a system is equal to zero, that is when it vanishes, we have that the total momentum of the system is equal to a constant. So it doesn't change with time. This was of particular importance for collisions because we usually assume that the collisions take place very rapidly. So during the collision, we can neglect all the external forces. Therefore, this leads us to the equality that the total momentum before the collision is equal to the total momentum after the collision. So we can relate the states of the particles before the collision to the states of the particles after the collision. Finally, we introduced the concept of the center of mass. This was a coordinate, an imaginary coordinate, which is a weighted sum of the coordinates of each particle in the system. The total momentum of the system was related to the total mass times the derivative, the time derivative or the time rate of change of the center of mass coordinate. So, and finally, this point, the center of mass, obeys an equation of motion. It moves as if it was a point particle where the net force acting on it is the net external force on the system. So let us now apply this concept of momentum conservation to the solution of some simple problems. You are familiar with the fact that if you throw something or if you push against something or someone, you usually experience a reaction force or a recoil. So therefore, let us see how this recoil velocity is related to the velocity of the thrown object using momentum conservation. Naturally, when you throw something, in order for this recoil to be noticeable, it has to be very fast. So therefore, let us look at the recoil of a rifle if you were to shoot a bullet with a rifle. Then you would certainly notice this recoil effect. So we have the situation here where before you pull the trigger, the rifle and the bullet are at rest. And then after you fire the bullet moves on with velocity little v, and the rifle recoils with velocity capital V. So let's assume that our positive direction is towards right. So, we are just denoting the magnitudes. So we know before the collision in this frame, the total momentum is zero because nothing is moving. So little mass times zero velocity plus capital mass times capital M times zero velocity gives us the zero vector for the total momentum. Therefore, this must be conserved since there are no other forces acting on this system. Let us therefore write the total momentum after the collision. So this is going to be simply mass times the velocity of the bullet, which is moving in the x direction, and then plus the momentum of the rifle, which is moving in the negative x direction. So let me write the total, its momentum as capital M, capital V in the negative x direction. So from this, we can equate the total momentum after the collision to the total momentum before the collision, and we find that the capital v, the speed of the rifle, is going to be little m over capital M times the little v, the speed of the bullet. So this was very simple. We can also ask, so how do the kinetic energies of the rifle and the bullet compare after the firing of the rifle? So the kinetic energy of the rifle is written here as 1/2 capital mv squared. So if I now substitute the result we obtained from the conservation of momentum, we see that this is going to be equal to 1/2 capital M, and for capital V, I write m over m v squared. So if you rewrite this, organize it in the following way. So I am going to cancel one capital M factor, and then group 1/2 little m little v squared. So I'm left with m over m capital M 1/2 little m v squared. So this is nothing but the kinetic energy of the bullet, right? So we can usually safely assume that the mass of the rifle is probably much bigger than the mass of the bullet. So we see that the kinetic energy of the rifle after you shoot the bullet is much less than the kinetic energy of the bullet. So this was the first example where we used conservation of momentum in order to find the velocity after the collision in terms of after the firing of the bullet in terms of the initial quantities. So let us move on to an example of a collision now. So we will classify collision into two categories. So in one type of collision, which we will call completely inelastic collision, the colliding objects move together, stick together, and move together after the collision. So let us look at this example here where we have a mass m1, a block of mass m1, moving again along a line with speed v1 towards a stationary mass m2. So let's assume there is no friction between the masses and the surface, and therefore this is our situation before the collision. So and after the collision, because this is a completely inelastic collision, the masses will move together, and let's denote the final velocity vf. So we are after this speed or velocity after the collision. So in order to get that, we can again employ the conservation of momentum, because we assume that during the collision no external forces are doing any work. So therefore the total momentum of the system is conserved. So let's write the total momentum before the collision and after the collision. So before the collision, we have just the mass of the first block times its velocity. So I'm just writing magnitudes. Let's again assume the direction to be to the right as positive. So it's going to be m1 v1 plus we have m2 times 0, because the second block is not moving. And after the collision, because they are moving together, we have the total momentum equal to the total mass times their common speed vf. So again, by equating these two equations to each other, we can solve for the final velocity, final speed of the blocks after the collision. And so let's do this in our head. So it's going to be m1 over m1 plus m2 times v1, which is the initial speed of the first block. Notice that writing it in this way, the fraction in front is dimensionless, so we have the final speed in terms of an initial speed, so which gives a correct unit. So in these complete inelastic collisions, the kinetic energy is going to be changing in general. Let's calculate how much change we have in kinetic energy in this example. So the kinetic energy after the collision is 1/2 times the total mass, m1 plus m2, times the speed squared, so which is the v final squared. So let me write this as m1 over m1 plus m2 squared, v1 squared, and from that I subtract the initial velocity, which is 1/2 m initial kinetic energy, m1, 1/2 m1 v1 squared. So we can do some cancellations here and again try to bring this into a form where we have a more transparent result. So if I cancel 1 power of m1 plus m2, so and bring this to the second term to the common denominator, so we see that m1 squared terms will cancel and I will be left with m2 squared divided by m1 plus m2. So let me write this as 1/2 m1 m2 squared divided by m1 plus m2 times v1 squared. And of course, we will have a minus sign, which is indicating that this is a negative change in kinetic energy. But I think I have made a mistake when subtracting, so let me correct this quickly. So m1 squared terms cancel, so from here I will have a factor of m1 plus times m2. If you want to visualize this completely inelastic collision in detail, so let us look at an alternative view of this type of collision where we can actually calculate this dynamics exactly and also imagine what's happening. So let's imagine here that the second mass was a long mass and the first block m1 starts on top of it with some initial velocity. Again, there is no friction between this long block and the surface. However, let's assume there is some friction between the first block and the second block. So what will happen is that as this first block slides on the second block, so it will accelerate the second block, and this is going to go on up to the point where their velocities are equal. Why is that? Because then their relative motion will be 0, and so there will be no kinetic friction between them, and then they will keep on with the same velocity. So therefore, if you look at it as a collision, we go from the first state to the second state. So these would be our before collision and after collision situation. So let's write the equations of motion for the first mass. So Newton's second law, F equals ma. So m1 times a1, the acceleration that will be equal to. So we have to draw some free body diagram here. So let's assume along the direction of motion we have just the kinetic energy. So I have including the direction as a minus sign. So m1 a1 equals minus fk. And for the second block, similarly, I have the same type, but now the reaction force is acting on the other direction, so in the opposite direction, so it will be plus fk. So if we integrate these and find velocities in terms of these accelerations, we find that the velocity of the first object as a function of time will be the initial velocity minus the force divided by m1 times t, and the second object will just accelerate with the acceleration a2, which is fk over m2 times the velocity. So again, we can now find the final time by equating these velocities to each other. So which is going to give us the following equation: fk over m1 times t is equal to fk over m2 times t at the time I called tf here. So we can solve for tf, right? So let me write it over here. So tf from these two equations will turn out to be m1 plus times m2 divided by m1 plus m2 fk times v1. Right, check this algebra. And therefore, the final velocity, which we can evaluate using either of these two velocity expressions, is going to be m1 divided by m1 plus m2 v1. Right, this is the same equation same final speed that we obtained before. However, we now assumed a concrete collision dynamics where we could calculate this exactly. So let's move on to a slightly more involved problem where we use conservation of momentum combined with conservation of energy to solve a more sophisticated problem. So let's imagine you wanted to find the velocity, initial velocity of the bullet that came from the rifle. A setup that can do this is the so-called ballistic pendulum, right, where you have a big mass M hanging somewhere and you fire your bullet in such a way that it hits this ballistic pendulum horizontally. Right, so therefore, and it will get stuck in it, so it will be a completely inelastic collision. And after that, you can measure how high this pendulum rises. Let's say it rises an amount h from its initial height, and we are asked to find, given these masses and the height, what is the velocity, initial velocity of the bullet, right? So in order to do this, we will apply the following. So from 1 to 2, so just before the collision and just after the collision, we are going to assume that the momentum is conserved. And then from that point onwards, we have only the conservative force of gravitation that we can express in terms of potential energy. So the total energy is going to be conserved from time 2 to time 3, right? So therefore, let's again write the conservation of momentum along the x direction, right? So let's assume the same things. M times v1, that must be equal to the total mass after the collision. They move together, and let's call this speed v. So, which is very easy equation so that we can find the speed after the collision, and then we apply from time 2 to time 3, we apply the energy conservation. So we can say the mechanical energy at time 2, which will be just the kinetic energy. So let me write 1/2 m plus m total mass v squared. So plus 0 potential energy. So let's take this as the reference of our potential. At time 3, when it raises, so it comes to a stop momentarily. So that's where the kinetic energy is 0 and the potential energy is going to be the total mass has risen an amount h. So I multiply mass with gh. So let us now use these two equations to solve for v0 in terms of the height. M over m plus m v squared. So this must be equal to 2 times gh. So I'm sorry, this is v0 now. So that v0 is going to be, so if I invert this and take the square root and multiply with the inverse of this, so it's going to be 1 plus m over m times square root of 2gh. So this was an application of conservation of momentum and conservation of energy in two different parts of the problem to relate the initial speed of the bullet to the height that you can measure of the ballistic pendulum. So here another interesting thing we can calculate is how much kinetic energy is converted to heat in this process. So in order to do this, let us again calculate the difference of the initial kinetic energy minus the final energy. So it's going to be 1/2 mv0 squared, which is the initial kinetic energy of the bullet, and the pendulum has 0 energy. So, and after the completely inelastic collision, I can calculate the energy either at time t2 or at time t3. So let's use time t2, so that will be just kinetic energy m plus m v squared. So that's going to give me m over m plus m times, if I substitute v0, 1/2 m v0 squared. So we have expressed it in terms of the initial energy. So you see, if the mass of the bullet is small, the change is almost equal to almost all of the energy will be converted to heat. So the second type of collision we will look at is the so-called elastic collision, where in addition to the momentum conservation, also the kinetic energy of the colliding particles is conserved. So in general, if you write in one dimension, if you write the conservation of momentum and conservation of kinetic energy, we will have two equations. And this is exactly sufficient to solve for the two unknowns after the collision, V1 prime and V2 prime, for these two masses, say. An alternative way, which is convenient in this case, is to look at a collision from an alternative frame, which is called the center of mass frame, right, which moves with the center of mass. Let us see how we can solve this problem by first going to the center of mass frame and then solving the problem easily in the center of mass frame and then coming back to the so-called lab frame, where initially our mass 2m is going to the right towards a stationary second mass m. Okay, so first I want to find the center of mass coordinate of the system and how fast it's moving. So it's going to be somewhere in the middle here. Let's again assume that the x-axis is along this direction of motion and the positive direction is to the right. So let us find the center of mass velocity for this system. So the center of mass velocity is equal to the total momentum divided by the total mass. So in this case, it's going to be 2m v1 plus m times zero velocity for the second mass divided by the total mass, which is 3m. So this gives us 2v1 over 3 as the center of mass velocity towards right, which I indicated here. Let us calculate the initial momentum and total momentum and kinetic energy for future reference. So again, if I multiply this with 3m, this is going to give me a 2m v1 as the initial momentum, and for the kinetic energy we have 1/2 2m times v1 squared. Once I have the center of mass velocity, I can find the velocities of these objects in the center of mass frame. So let me call them v1 center of mass and v2 center of mass. So I'm expecting the second mass will be moving towards the center of mass because their total momentum should be 0. So how do I find this relative velocity? It's going to be the relative velocity in the lab minus the velocity of the center of mass with respect to the lab. So this is going to be v1 minus 2v1 over 3. So I find that the first mass is moving with v1 over 3 towards the center of mass. And for the second one, we have initial 0 velocity minus, so v2 minus v center of mass, v2 center of mass, the v center of mass, also for the second mass. And then this is going to be 0 minus the center of mass velocity, 2v1 over 3. So this gives me 2v1 over 3 in this direction. So how am I going to find the velocities after the collision? So after the collision, let me denote these velocities with primes, so v1 prime and v2 prime. So the center of mass, in the center of mass frame, so I'm expecting them to go in opposite directions with v1 center of mass prime and v2 center of mass prime. Right? So since I want to conserve both momentum and kinetic energy, you see that solution will be if I just invert the velocities to their opposite directions with the same speed in the center of mass frame. So why is that so? Because first of all, the center of mass momentum will be again 0, and also by calculating the kinetic energy, because we are squaring the velocities, the kinetic energy will also be conserved. So therefore, I want the total momentum in the center of mass frame to be 0 before and after the collision. So I'm going to take this solution that we argued by just changing the direction of the velocities in the center of mass frame. So I'm going to take a v1 center of mass prime as minus v1 over 3 and v2 center of mass prime as minus 2v1 plus 2v1 over 3. So therefore, finally, going back to the lab frame, finding the velocities in the lab frame after the collision, v1 prime and v2 prime, I just add the center of mass velocity to go to this frame. So it's going to be minus v1 over 3 plus the center of mass velocity 2v1 over 3 and then for v2 prime, it's going to be 2v1 over 3 plus the center of mass velocity 2 v1 over 3, right? So which gives me 4v1 over 3 for v2 prime and v1 over 3 for v1 prime. So our original choice of directions was therefore correct. So let's calculate the total momentum very quickly to check. So after the collision in the lap frame, I have 2m times v1 over 3, and then we have plus m times 4v1 over 3. So this is going to give me m times 6v1 over 3, which is nothing but m times 2v1, right? So it checks with our initial momentum. So as for the kinetic energy, we have 1 over 2, 2m v1 over 3 squared plus 1 over 2m times 4v1 over 3 squared. So if we calculate this, this is going to be 1 over 2. So I have 2 over 9, and from 4 I have 16 over 9. So altogether this gives me 18 over 9 v1 squared. This is again 1/2 2m times v1 squared, which is equal to our initial kinetic energy. So in this type of collision, we have seen both kinetic energy and momentum are conserved.